So how do we know the strengths of acids and bases? Well, if we take something like HF as an acid, it's going to react with water, and the acid is going to donate a proton to produce H3O+. Because it's an acid, it acts as an acid. And so how do we know the strength of this acid? Well, we can look at the concentrations of all of these products at equilibrium. And when we talk about at equilibrium, we always know that we can talk about the value of the equilibrium constant. And so the equilibrium constant is going to be the concentration of the products. They're not raised to any particular power because in this particular instance there's only a 1 in front of each of one of these. And then this is going to be divided by the reactants and the concentration of HF, which is the acid in this case. And of course H2O, which is a liquid, does not appear in this equation because H2O is a liquid, has an activity of 1, therefore it does not appear. And these concentrations are concentrations at equilibrium. And this value of K, we give it its own little term now because it's specific to an acid, and so this is what's known as the acid ionization constant. And it's exactly the same as the equilibrium constants that we've talked about before, but because this is specific to an acid at equilibrium, it's called the acid ionization constant. And so if we were to look at a sort of a general acid here, so a general acid HA, it's going to react with water. This is going to donate a proton to H2O to produce the hydronium ion, and this A minus. So in this particular case, when we talked about HF, this A was represented by F. So if we talked about HCl, this would be the chloride ion. If we talked about HBr, this would be the bromide ion. And so for a general acid, we can say the auto ionization constant, Ka, is going to equal the concentration of hydronium ion, the concentration of A minus, which of course this is the conjugate base of this acid, divided by HA. And so this is for a general acid, so we could add any type of acid that we wanted. And remember, these concentrations are at equilibrium. And so what's the point of this Ka? Well, this Ka is going to give us a great idea about how strong an acid is. So for example, if the equilibrium was sitting on the right hand side, if in fact most of this HA, this acid, had donated protons to produce H3O+, this equilibrium would be to the very right. And because it would be to the very right, the concentrations of the products would be very high and the concentration of HA would be very low. So a high number divided by a low number would give you a large value of Ka. So if the value of Ka is large, it means that the equilibrium favours the products. And in this particular case, because we're talking about acids, this would deem this to be a stronger acid. So large values of Ka tell us if it's a strong acid. Conversely, if we have Ka very small, this means it's a weak acid, meaning that most of the reaction is on this side, on the reactant side. And so Ka values give us an idea of how strong a particular acid is. Not surprisingly, if we look at bases, so it's exactly the same thing. So here's pyridine, which is a base. Pyridine is going to accept a proton. And where is it going to accept a proton from? Well, it's going to accept a proton from water, which in this particular case, acting as an acid, because donating a proton. And so the base accepts a proton, and when it accepts a proton, it produces the conjugate acid. And so if we look at a value of the equilibrium constant, and because we're dealing with a base, it's called Kb, because we're dealing with a base, and so it's the concentration of these two products, divided by the concentration of pyridine, the base. And of course, water, so liquid, doesn't appear in this equation. And these are the equilibrium concentrations. And so we could also say for a base, for a general base, here's the base, accepts a proton from H2O, which acts as an acid. It produces Hb+. So in this particular case over here, this is what we see. And then we have this OH- ion, which is not surprising, because when we talked about Arrhenius and Bronsted-Lowry definitions, we often saw this OH- in the presence of bases. And so the value of Kb, which, because it's at equilibrium concentrations, it's given the term Kb because it's the base ionization constant, because we're dealing with a base. And so it's the concentration of the products divided by the reactant. And so again, if Kb is very large, that means this reaction is towards the products. There's a lot of OH- produced. There isn't much base left. This Kb is very large, which means you have a very strong base. So things like sodium hydroxide, potassium hydroxide are going to have very large Kb values. And so that's the reason why we use Ka and Kb values, because they give us an indication of how strong an acid is. So a strong acid is going to have a high Ka value, a strong base is going to have a high Kb value.